So this project is about estimating free energy difference, and I will begin first, and then I will hand over to Yuanqi. Also, I would like to thank my collaborators, Francisco, Yuanqing, Carla, Miguel, and Eric. So here is a little background about this. We normally define this anomalous density through some energy function in this way. And there is a term missing, which is known as normalization factor, which is defined as the integral of the anomalous density over the whole support. Then putting on top of that, we take the logarithm and take a negative sign. And this thing we normally call it free energy. And the free energy difference, sometimes we have more than one system. If you have two, we might care about the free energy difference between these two systems. So this is defined as the logarithm of Z2 divided by Z1. And why this thing is important is because we have already seen this a lot of times in different aspects. In classical Bayesian inference, we know there is term model evidence, which reflects how well the model captured the data. And that thing is just free energy, actually. Or actually, it's a normalization factor. And also in biology, in molecule, it's like binding affinity. And also in molecular simulation, we care about potential of mean force, which is also the free energy surface. Because this thing is very important, there are a lot of historical methods estimating this free energy difference. I think the most classical and most well-known one is the FEP, free energy perturbation. This is actually just standard important sampling. And if you look at this definition of the free energy difference between two systems, we realize that we can plug in the definition of that two. And then we do normal important sampling. We times P1 and divided by P1. We recognize this P tilde 1 divided by Z1 is just normalized density of P1, which is good. And another term is just the energy difference. And then we can write the whole thing into expectation of the first system. And the inside expectation is the energy difference. And building on top of that, we can do bar. This is the minimum-variance estimator, and it runs in an iterative fashion. Basically, the form is like this. Here, the C and G are actually general. C is a general constant, and G is a general function satisfying this expression. And to have a minimum variance estimation, G, we take the Fermi function, and C should be delta F. But we want to estimate delta F, right? So it's not possible we can set C to delta F at the beginning, because that's why the iterative algorithm comes in. We first initialize C to some value, then we estimate delta F with the C, and we set C to delta F and calculate again until convergence. So both FEP and bar are actually based on important sampling. If you look at FEP, it's just two. If you look at bar, it's just two FEP. FEP is just important sampling. And that means that if you suffer from this kind of overlapping problem, so if you have two distribution overlap, okay, that's fine. But if you have two distribution that has no overlap, the estimation will be super bad, right? So one way to increase overlapping is to do mapping. For example, if you have these two distribution, we learn a bijection. We map P1 to this P1 prime. This P1 prime can have like, it's not necessary to be P2, but it's aimed to have larger overlap. And this is known as target FEP. And if you look at the standard FEP equation, the target FEP is actually the same, just introducing a change of variable. So it's just like the FEP between P1 prime and P2. And for this projection, you can design it manually, or you can learn by knowing the flow, you can learn by flow matching. Another way to increase overlap is to do annealing. It's quite standard. So assume we want to estimate the free energy difference between P1 and P2. and we now plug in a lot of intermediate distributions. And now each of the neighboring has enough overlap so that we can apply like sequence of FEPs. And actually, you can show that if you take the limit, which means you have infinite many distributions plug in, insert in between, you will recover this thermodynamic integration, or TI. Basically, it says that if you get sample from every intermediate distribution PT, which is defined also with this U, then you can take the expectation over its partial derivative over U and take the integral from 0 to 1 to get the free energy difference. This is known to be equilibrium because we need sample exactly follow this PT, which is proportional to the exponential of the negative UT. So this can be expensive. And people will ask, okay, is there any non-equilibrium algorithm? Here's this Jarzynski equality comes in. This is a very, very famous non-equilibrium approach. To understand this approach, we first look at the classical annealed impulse sampling. So we still, Hannes, you are muted.
Yeah. So can you go back and elaborate a little bit on why we call this equilibrium sampling? Like we now have a changing density. So why is it equilibrium sampling if we like have samples whose density?
Yeah, so basically it depends on path from 0 to 1. And on the whole trajectory from 0 to 1, the sample needs to follow the energy you define. Like
Okay,
if
so
your energy interpolates between 0 to 1, does it make sense?
the point is that at each intermediate distribution, we have samples that are equilibrated.
Yeah, yes, you need sample exactly following this distribution.
Yeah.
Yeah. Okay. So yeah. So for non-equilibrium approach, let's begin with a new impulse sampling. Still, it's the same. If you have some distribution, there's far away from each other, we put in a lot of intermediate distributions. And then to perform so-called anneal impulse sampling, we first draw a sample from P1. This is the exact sample or an equilibrium sample. Then we start to evolve the sample following this Amsterdam's kernel. And here I write in this way, saying that Amsterdam's kernel is with the invariant density as PT. So we define the whole thing as a forward pass. And similarly, we also define backward pass. This we will never simulate this pass. We just define this so that it's as a target to do impulse sampling, right? And note that this forward pass and backward pass, they share the same Amsterdam's kernel at each time step t. This is important for impulse sampling because this will allow us to cancel something. But actually, we will shortly see this is not very important for us to define the impulse weight. And so if we write this kernel in this way, we will have so-called detailed balance. And now this F and B are actually the same kernel. I just write in this way. So to emphasize, it's for forward, it's for backward. They are the same kernel that specify this detailed balance. And instead of doing impulse sampling from P1 to Pn directly, we actually do the impulse sampling from the path going from P1 to Pn with the target going from Pn back to T1. So this is the prior or the proposal. This is a target. And then the density for the proposal is just to multiply all the transition kernel and the starting point together. And the target is also multiplying the things together. And then the density ratio, or here the impulse weight, is defined, just the ratio between these two likelihood, two densities. And we also plug in this detailed balance to simplify things. And if we do so, we can show that you can simplify it a lot. Actually, all the transition kernels cancel out. You only live with the marginal, the ratio between marginals. And also in log space, we can write things in a concise way. Okay, with this important sampling weight, how can we estimate the free energy difference? So here is the observation. Because normally our transition kernel are normalized, or even though it's not normalized, it's share the same kernel, normalization factor is the same. So that means the delta F between the first distribution and the last distribution is just the delta F between the forward process and the backward process. So now we put everything together for a new independent sampling. There's nothing new here. It's just rewriting things. This is forward, this is backward. This is the log ratio or the importance weight. And this is the free energy difference. And we applied FEP equation for the free energy difference. We input this, we plug in this definition, and we also do important sampling. And here we plug in the definition of this important sampling weight, right? To simplify things, we call it W. We will get this expression. And also we recognize this thing is a normalized density, which means we can write everything into expectation. So now we get things in this way. So delta F become this simpler, this very, very simple equation respect to this W. And actually, just as I mentioned before, we do not really simulate this forward process, this backward process. We just use it as a target. And after we cancel out everything, we do not really need this target. So let's forget about this. If you put everything here, we will see this is a very, very clean expression. We just follow this forward process. We calculate this W, and then we use this log mean F to calculate delta F. And now, if we change this MCMC from a general MCM kernel to unadjusted Langevin, and note that unadjusted Langevin only makes sense when you have very tiny step size. Basically means that you almost have infinite many intermediate distributions. If you do so, this unadjusted Langevin actually become a forward stochastic differential equations. And also for this W, if you do this limit, you recognize that this difference become a partial derivative with respect to t. The summation become integral. Now let's replace everything by this new infinite many intermediate distributions version. You recognize this is the well-known Jarzynski equality. So basically, it says that you follow a forward process, a stochastic differential equations, and you calculate the work along this path, and then your delta is related to this work. And this is not accurate because actually, if you follow this process from x0 to xt, and you look at the density for xt, you will see it does not really follow pt. The pt is defined by ut. So that means it's different from the thermodynamic equation we have already seen. For that thing, it will require xt to exactly follow pt. Here, it's just required to simulate, and whatever you get, that's fine. But even though it's fine, even though this estimator is always correct in expectation, that doesn't mean this works well in practice. If xt deviates too much from ut, then this expression can have large variance and also bias if you have only finite number of samples. So to solve this problem, people introduce a control term. This is known as escorted Jarzynski equality. So here, compare these two expressions, we just plug in a u, which introduces more flexibility. And then also to compensate for this influence of this u, we need to change this work to a generalized work version by introducing these actual terms. So by carefully design or learn this u or anything to make u better, you can get an xt that getting closer to pt. In this way, you can reduce the variance of the estimator and also the bias. And also there is a Crooks fluctuation theorem for Jarzynski. And here for escorted, this also has this controlled version of Crooks fluctuation theorem. It basically says that if you have a forward process, we just seen for Jarzynski equality, we can also write down a backward process in this way. So the only difference is that the control term is the same, and you change the sign to plus to positive. and you simulate backward. And dt is also negative, right? So if you write this forward process and backward process, this w in this general form can be written down as the Riemann-Nikodym derivative between this measure and this measure. And this can be just think about is just like density ratio. So one thing I want to note is that this thing and this thing is not necessary to be time reversal. So in diffusion model, we know that the forward process, backward process, when we learn perfectly is time reversal, then it works well. But here that's not really necessary to make them time reversal of each other. It's just like one way to reduce variance. Even though it's not time reversal, everything works perfectly fine. And if it's time reversal, then actually all the xt will follow the ut. So basically, escorted Jarzynski is very good because it's non-equilibrium. It has higher flexibility by this u. So we want to use it by learning a transport between two states we want to estimate. So this problem setup is very simple. Assume we have two systems, U and UB, and now we get access to samples from PA and PB. So this sample assume is very cool dog. This sample we assume is good, exact sample from this equilibrium distribution. We estimate the Brand difference by escorted. Now the question becomes, if we want to use this escorted version, we need learn a transport in the form of the forward SD and backward SD. And the drift is like the nabla u plus the control term. So how can we efficiently learn this thing? So one thing, if we want to learn ODE, we know that flow matching is very good. If we want to learn SDE, we can use a stochastic version, which is known as the stochastic interpolants. Okay, so basically, this is the short, very brief introduction to SI. I guess everybody somehow know a little bit about it. Basically, we want to learn some process in forward in this way. Like you can just imagine it's like a vector field plus some noise. We have a sample from both ends, and to learn this, we first draw a sample from both ends, and then we also draw a noise. And here I just write you draw sample from the product space, but actually you can also draw from you can also define a plan like OT plan or something else to make things easier. But it works for general pairs. And here, after you got x0, x1, and the Gaussian noise, you can define this stochastic interpolant in this way. Actually, I write here just a specific realization. This coefficient, and this coefficient can be something else as long as this satisfies going from 1 to 0, this going from 0 to 1, this going from 0 to 0, and some non-zero value in between. So you can define, for example, cosine, sine, something like that. After you got xt, you can learn this ut, this vector field, by matching the time derivative. It's just like how you do flow matching. And here, this u is a score, so we can learn by denoising score matching, or even target score matching. And here is the illustration. This is like OD, this SD version of it. After we learn this vector field, we learn this energy path. We can estimate free energy using this Jarzynski equality, control Jarzynski equality. And note that we have two versions to write this work. One is to estimate this one, another is to using this forward and backward path measure. Also, we have two expressions for this delta F. One expression you can go forward. You can just use this as your main simulation process, and you get this expression. Of course, if you have data from another side, you can do backward, right? You can simulate this backward, and now you just estimate. You can do the same logic, but estimate minus delta. That's why you can have this almost symmetric expression. Yeah, so in summary, the method from a very high level is like you want to use stochastic interpolants to learn this transport between two sides, and then want to calculate this generalized version of work, and finally we use this escorted version, escorted Jarzynski or control Crooks version theorem to calculate the free energy difference. And one thing I also want to note is that here, using stochastic interpolant actually has some advantage, because normally when you think about defining path in a classical way, you might consider defining like geometric interpolated path, or sometimes you want to define like physical path. But actually, we don't really care about how this path looks like. If you define this like geometric interpolant or other interpolants, it might make the training a little bit unstable. For example, if you only have data from two sides and you define the geometric interpolance path, and you can only train it with like KL divergence, log variance divergence by doing the simulation or the whole process, taking gradient along this process to calculate W, for example. This can be expensive, and also we know that geometric interpolant has some bad property. For example, the teleportation issue. Basically, says that only when you get very close to your target, your mode weight get correct. Otherwise, it can be wrong, and this will create very bad vector field, making things very difficult to learn. But here, because we define this U and this control both by this stochastic interpolant, and we learn them both, actually this thing can be much easier. So this is why our design choice is like this. Okay, this basically the high level description of our method. And is it everything? Well, actually, it's not. So there are some practical consideration, including the numerical thing, and also the calculation, the computation thing, and also like boundary conditions. And from this, yeah, after this slide, I will hand over to Yuanqi. Is there questions?
Yeah. Why do you not just learn okay, first of all, why do we call it U and U? No, never mind. So why
Yeah,
do
sorry,
you take the why don't you just learn the little U, and then you can still do the same stuff, just in your equation for your W, the first two terms now fall away and you only have the third term, and that also works, no?
Yeah, I think what Hannes refers to is like a KL. Like that's what Jiajun mentioned, right? So we can define a geometric interpolant which we fix UT, well, like capitalize the UT, and then we only learn a control. And the issue is like it's hard to learn with KL, and also it requires you, when you learn it, it requires you a lot of energy cost with UT, right? Where here we interpolated that like in the probability distribution, and we don't have access to any UT. So the score is actually learned.
I think is what you're asking, like
you
just train with flow matching, so you just have the flow, and then you just like integrate the divergence and then reweight it at the end.
You just have a deterministic flow.
Oh, okay.
That thing is actually one of our advantages. As Yuanqi will shortly introduce, we don't really want to use this expression. We actually use this expression. It's much cheap. It's cheaper than this thing, because you need to evaluate divergence.
Yeah.
Yeah. So actually, we if we set this sigma to 0, you can see we recover flow matching. This is one of the connection from our method to others. But in practice, we find this thing is much easier to calculate. This is just calculating this transition kernel. And for flow matching, you need to
later on will have a trick with which you can get rid of computing this divergence, and yeah, we only need to we have some other estimator for this ratio that doesn't require computing a divergence.
So in our method, we don't compute the divergence actually. We just use this control Crooks. And for flow matching, I mean, there are also tricks like trace estimator, but it does not work very well.
Well, then that's sort of the advantage that we'll get into now. Let's hear it.
So then if there's no more questions, I'll hand over to Yuanqi. Okay.
I think okay. Yeah, right. Got you.
Yeah, I'll stop sharing.
Yeah. Okay. So yeah, as Jiajun mentioned that. Okay, can you guys see my screen? Perfect. Okay. So yeah. So next I'm mainly going over. Yeah, exactly. The point was, we have two estimators. One is like this kind of changeable variable with control correction, and the other one is like this forward backward SD. And we want to argue why we should use the SD, the stochastic dynamics as the estimator for work. So there are a few reasons, I think. So first, by looking at this, yeah, so the work can be, so on the right-hand side, what Crooks fluctuation theory tells us is like you have this log density ratios. Notice here P left and P right are normalized. And this delta F is the normalization constant on the boundary. Which what you can do is actually you can expand this term and you can denormalize you can expand the normalization count, like the free energy difference on the boundary, and then you can expand it and you can denormalize it. And so this, and that's also kind of like a that also provides additional advantage. But this is in practice how you calculate it. So you have so we have access to UA and UB, which are the Hamiltonian to the system A and B, which we can evaluate, and we also have samples. Okay, I think I have to, I'm not sure if we emphasize enough. So the method requires samples from both sides. As you can see it in a bit, because I think Jiajun already warmed up a little bit when he talked about this free energy perturbation method. So you can actually you can estimate the free energy difference from sampling from system A and weight it with the energy difference from both system, or you sample from system B. And similar here, you can actually go forward from A to B. You can also go backward from B to A. That provides you two estimators, and there's extra degree of freedom that you can handle to have a minimum variance estimator at the bar method. But the point here, so that's why like the state of art method for estimating free energy is leveraging this bar, and that is our setting too. So we do require access to samples from both boundaries. Just want to emphasize. So we can evaluate this boundary energy ratio, and then we have additional this forward in discrete time Gaussian and backward Gaussian kernels, and then in reality what it does is like we essentially just evaluate these Gaussian kernels from the forward and backward SD. And notice that to evaluate this, we do not require the energy of intermediate time. We only require the score, which is what we learned. So we don't need, for example, there's a method called neurothermodynamic integration, where they have to use the energy that learned by the. You need an energy parameterization of your diffusion mode or stochastic interpolant. I won't argue if it's that bad, but usually score parameterization works slightly better. And this is one thing. And another thing, as we emphasized, with this forward-backward R&D, there's no divergence appeared in calculation. And in fact, if you really want to evaluate the divergence, it's really slow in practice. With some approximation can be faster, but it can be less accurate. And what we want to do is like we want to avoid it. And then, yeah, as I already said, like you can go either forward and backward, and this already provides you a sense of, oh, this is not exact what the bar should like, but this already kind of give a sense of a little bit that we have extra degree of freedom of how to estimate free energy difference with this log mean x estimator from both forward one distribution weighted another or another distribution with this. And this is kind of like the bar method generalized to path matter. Also, this is not new. We derived it, but this has been derived before. And then you have minimum variance estimator for 9 kilogram sampling. and G here, the actual flux bit is also the Fermi function, and the constant C can be anything, and the optimal is delta, the free energy difference, and then same procedure, and this gives you another estimator. And in fact, now we have two estimators. One is like this forward log mean x estimator, and the other backward log mean x estimator, and we also have this bar estimator.
Yuanqi, can you go back a bit? One more slide where we come up with this W.
This W is the
like this where we come up with the W.
That's from the. Sorry. Go ahead.
Okay, so this W is kind of like the ratio between forward and backward SDE, like this density ratio along the path. It's exponentially the W, so you take log, so that gives you can consider as importance weight.
Yeah, but can we please go back one slide where we come up with this forward and backward?
Yep.
So it's controlled Crooks fluctuation theorems. Basically says that this W in this kind of ODE integration form can be written down as this forward backward ratio.
Yeah, okay. Can we go one slide? Yeah. Okay, I'm not sure what's going on.
It's like normal bar.
Yeah, so we do, yeah, actually W is work. Yeah, it's generalized work. And the exponentiated W is the importance weight. So here, what's going on is actually, so this path, that's the ratio is on the boundary is normalized, and then we luckily we have a free energy difference there, which gives us the normalization boundary on the normalization constant on the boundary, and then we denormalize it, and then we don't need normalized density on the boundary, which we don't access to. We only require the energy.
Yeah. Okay, I'm happy.
Okay, sounds good. All right, and then where was that? Okay, this bar estimator is the same mechanism from bar method applied to here, and yeah, and here here. Okay, so again, so we don't want to calculate a generalized work with the ODE, which I think it may recall the same thing as in the non-equivalent transport sampler paper, the ODE. We actually want to calculate this, estimated the work by using this forward, backward, random equivalent derivatives, and any other practical concerns actually. So if we look at this ODE thing again, we can see there is a partial TUT term, which may not be agree with the true boundary. Okay, first of all, it requires energy parameterization. What we learned from, so because for stochastic interpolant, the score that you learned, okay, let me. So for stochastic interpolant, you parameterize the energy as a score that you use energy to parameterize the score. So that induces the energy. So you need to use what you learned by a neural network, this UT, and this may not agree on the boundary because your boundary is UB and UA. So when you learn it, you never kind of like strictly enforce it, right? So. And then if it's with imperfect boundary conditions, then you have to make a correction. So you do integrate from neural network, but there's a correction term what your neural network induces this U1 and U0 from here, and then you have to reweight it. Come on, you cancel it out, and you reweight it to the correct boundary UA and UB. Yeah, this is this doesn't induce any computational inefficiency that much, but it's just like something you need to handle. There's imperfect boundary condition, which in Crooks fluctuation theorem you don't, because you're already using the perfect, like the boundary that you expect. Yeah, so that's another practical reason why you should use it. And another practical reason is about discretization error. So in fact, so this everything is in continuous time, and how do we discretize it? So we first discretize the forward and backward SDEs with just Euler, and next for the ODE, we have to discretize the ODE again, right? So once we discretize the ODE, that introduces another discretization error. But with the forward backward R&D, so you already discretize your SDE, so you just use the same discretization for XT. You don't need the actual discretization for your work, and that gives you it could be biased that comes from this discretization error from the work ODE, but and the SDE, it doesn't require this. All right, so there are three. Okay, so to summarize, there are three benefits that we are talking about. And first, with the forward backward R&D, you don't need to learn the energy, you don't have to parameterize it, and you don't need to calculate divergence, and you don't have to correct for the boundary, and you don't have bias from discretization to work.
I kind of missed the discretization fix. Can we look at that slide again?
Yeah.
So do you just have a reweighting at each step or something?
Right, you just have a Gaussian kernel at each step. So this XT is already discretized from here.
I think it's helpful to think about importance sampling. So if you do importance sampling, there is one requirement that your proposal is that thing you put in the denominator should be equal to the things you put outside the inside the integral, the expectation, right? Like you take respect to Q, and it should be like P divided by Q. This should be the same Q. And here, note that when we do simulation, we already discretize. Basically, this says that your proposal is already a discrete version. And note that this W2 also put this discretized version in the denominator. So that they align. Yeah. So there's no bias, so introducing bias.
Basically, we basically add a possibility for transitioning by changing to this other point by changing the process to include these random steps, like these random Gaussian steps, and then we compute the likelihoods of these random Gaussian steps forward and random Gaussian step backward, and then their ratio corrects. Yeah, okay.
Yeah, that's exactly the idea. Right. So yeah, so the three benefit, and first a bit of a connection. Last a bit of a connection to other approach. So so this is as we showed before, like this is our forward process. We're not writing the backward here, but you can see like if you cancel certain things out, it gives you a different method. So for the straightforward one, it's just like if you cancel out the noise, it gives you the target FEP with flow matching, for example, which means this terms out and this noise terms out. You just have a vector field that can be flow matching, and it can be further be FEP if the velocity if you don't have a velocity, so you just do importance sampling. Okay, sorry, here should be U. And with the bar, if you, okay, that's trivial. You have a minimum variance estimator that gives you the bar already. And with thermodynamic integration, and that's interesting because that's when you learn this perfect UT, that means like you have already, so each time marginal induced by this SDE that has a invariant density that comes from UT from energy. So that of course, so because it's non-linear process, but it induced like equilibrium marginals, so that also recovers thermodynamic integration. And yeah, and just looking at this along with it's just normal Jarzynski equality. If the control is zero, if don't learn the control with perfect boundary, and then if the control is non-zero, if you have the control term, that's the controlled version of the Jarzynski equality. And this is just some connection. And we've done a few experiments on multiple systems, kind of like to show how it works. And there's first is a Gaussian mixture. You have 16 moles on one side at the boundary and 60 mole at another boundary. And you can raise this to 40 and 100 dimensions. And for Lennard-Jones potential, we have systems that without the interaction, the potential or with the potential, and we have ionized dipeptide solvation, which from one system with in the vacuum and the other system in implicit solvent, and the last one is the phase transition, which we have one mode of the ionized dipeptide, like one metastable state and another metastable state. And so here is what the results look like. There are numbers. I'm just going to reading it off. So the reference value is we consider as ground truth is that we run M bar. So we kind of like put multiple intermediate distribution connecting these two energy. And then we sample from equilibrium of them and make sure we well equilibrate. And then we use M bar to estimate it. So it can be considered as a multi-marginal bar method. Is what people use in practice. And okay, for GMM, of course, the reference we have ground truth is just normalized, it's 0. And this D means the dimension. And the Lorentz we have this 55 particles, 78 particles, and we add additional kind of quite hard one, 128 particles, and analyze 22 particles. And we compare with target FEP with flow matching. I think for some simpler system, it works okay, but it gets very bad when you have larger system because the divergence. Okay, here we didn't use any kind of like approximations to divergence, and with 55 dimensions, it's even almost uncomputable. It takes more than a day to compute the free energy difference, but of course it can be done better. But for LNI, you can see if it works, if it can be calculated, it's okay. And neural TI is a method that using energy to parameterize the essentially initially use diffusion, later on they use stochastic interpolant. But the idea is like to learn a transport from two distributions, well, to use energy to parameterize the score. Once you have this energy interpolation, then you have then you can use thermodynamic integration on this energy. And for GMM, some of them can be quite bad, and yeah, and we cannot produce reasonable result for Lagrange with more than 100 dimensions. And this is our method, but okay, mostly what this is showing is like oh, by the way, so all the values in this table is unitless. So it doesn't get multiplied by kBT, the constant. It's just unitless. And yeah, essentially what we want to show here is like we can, for this kind of system, it works within certain accuracy. And we can look closer about the estimator. So we show the hard example actually. This Lagrange's 128 particles. There are 3 lines here. So the right lines are actually the log mean X estimator that are actually lower and upper bounding. And this in the middle, this black line is black dot dashed line is actually the reference value, and the x-axis is the x-axis is the number of training iterations, and the blue one is the minimum variance estimator. As you can see, even when we just train very small amount of iterations, this minimum variance estimator can already be pretty accurate compared to if you use just the regular this log mean X Jarzynski equality estimator. And similarly for this ionized dipeptide solvation, you can see like this minimum variance estimator converge much early than the regular estimator. But yeah. All right, I think, is there any question about the experiment or something? And then I'll wrap up.
I think there is a question about neural TI results. I was just typing to reply. So the result is very bad compared to what the authors show in their paper. The reason is that in their paper, if you carefully look at it, they designed a network with the precondition with the ground truth energy from both sides. So basically, it ensures that the boundary condition is satisfied, and also in the path in between, the energy will not go crazy. But here, to give a fair comparison, we use almost the same network architecture for the 3 methods. That basically means that there's no preconditioning, there's no enforcing boundary. We just try to learn it well, and actually it said that it cannot learn very well. That's why it have a large deviation from what we expect.
Okay, I saw another question about for multi-state setting. In fact, there is, but I guess yeah, we can chat more about this later. But I guess what the goal is, because the point we are trying to do here is like we are trying to do transport instead of having multiple marginal in between. Because for free energy estimation, if you have boundary data from two boundary, all you care is like if you have a good transport that from one distribution, one boundary to another, that have a decent amount of overlap with the other, right? So I mean, if one can already give you good results, then you don't have to do multiple. Then you requires data from multiple boundary. That's kind of like the difference from our method to M bar. We can certainly do kind of like a multi-state, but the issue is when it becomes useful that we should do it, right? So because M bar it requires kind of like multiple state in between that you sample from equilibrium, but here we actually don't. All right, sounds good. All right, then I'll summarize and wrap up. So to summarize, we propose a non-equilibrium approach to calculate free energy difference. So so the main contribution is actually realize a way to learn the transport with these stochastic interpolants that are scalable, and as far as we know that they scalable to large systems compared to for example using reverse KL and to learn samplers that's less scalable. And it's a realization of the escorted Jarzynski equality learned and how to do it. And we use and advocate a bit on using the forward backward R&D to calculate work because it has nice benefit. And in the end, we use the minimum-variance estimator, which converge quite fast and stable. Yeah, and the comparison to other baselines with neuro TI, we are non-equilibrium, and they are equilibrium. They learn the energy, and then they sample from they do TI essentially. And with neuro-targeted FEP, which people use normalizing flow, and I know Hannes also played with flow matching and others. And we thought it's easier to calculate the work. And with M bar, yeah, we don't have intermediate distributions, and hopefully neural network is generalizable, and but it induces cost when training neural networks, right? So, and yeah, and for larger systems, solvent and those things, alchemy, we haven't done it really, but yeah, we're testing on some of this. All right, so there are some references that are classical method, like the seminal work of FEP, target FEP, bar, and Jarzynski, and everything like also this controls Crooks fluctuation theorem and escorted Jarzynski that are recently kind of like proved and revisited, and in the interest of neurosamplers, and also other neural network based approach like this neural target FEP from DeepMind, and yeah, and many others. All right, thank you guys for joining us.
Hi, Francis Sun again. What did I want to ask? Right, time. So, right, what if I just put now some intermediate distributions to my free energy perturbation where I simulate all the intermediate distributions, then take my bar estimator and compute the free energy difference that way. And I mean, yeah, I have to simulate a bit, but probably that's pretty quickly done for the same size systems. And then maybe that's even faster than training your flow. So like like how do you plan to make comparisons between training time versus simulation time if I have a free energy perturbation versus your stuff?
We haven't had that yet, but I think we will try to include it. But yeah, so it could be tricky because people usually when they do M bar, they don't just run independent MDs like at different energy level. So they use some like parallel tempering. They use some method that can give you samples more efficiently using one to help another. So that's actually a very good point. Yeah, it's so the main comparison we did was with neural network approach before, and to show what you can do much better. But and we set M bar as our ground truth. So yeah, we will try to compare with M bar for sure. In the following, and also I
And
saw
one thing.
Go ahead.
Oh, sorry. And one thing related to this question is that we can give some rough time value. Like for example, for L9, running it to equilibrium takes like less than 1 day. It's definitely more than half a day, I think, half a day to 1 day. For training network, if you look at the plot we show, like the convergence of the things, it converges very fast. So if you cannot running all the intermediate states in parallel, then this means that once you have the samples from two sides, then you can train this network fairly fast to calculate free energy difference. But also this thing will scale up with your system. For example, for very complicated system, the training might take ages, which I don't know. Yeah.
So one thing there is then also, right, we can parallelize and we can simulate all of our intermediate distributions at the same time, while your neural network training is sort of is as fast as the neural network training is. And now I know that when running free energy perturbation, like some standard setups, and I just download the FEAT software from, or like there are some GitHub repositories where there's fast FEAT software implemented, and then I run this for actual molecules and transforming one molecule distribution inside of a protein pocket into a different molecule distribution inside of the same pocket. This takes like 4 hours, and now we're sitting here and training our neural network for alanine dipeptide for more than half a day. Yeah, of course, right? The difference. I just want to. I'm not saying that this is not worth looking into. I'm just saying that or providing additional perspective. That's yeah for others, and but I think, and that's why I myself like look into this a little bit as well, right? I think it's very interesting if we can maybe push these methods, how far we can push them, if they're maybe more flexible than like for these free energy perturbation setups. I think it's always the case that you might have some slight setup problems, and then everything breaks down. You have super high variances in your estimates and can't get a reasonable free energy difference estimate. And maybe this here is now much more modular, or much more, not modular, more general, and works well for all systems and doesn't require much manual fiddling around. And then if we can get it working well as well, then maybe this can be something like a much more plug-and-play solution than what free energy perturbation is right now.
That makes sense. Yeah.
But Ezra, you had a question?
Oh yeah. So I apologize if I missed this earlier, but I was wondering if you take basically the data that you train with for your stochastic interpolant and you just compute the free energy on both ends just using those samples. How good is that estimate compared to the estimate of the model that you get when you train using those samples?
I think for this discussion, I'll throw in a thought experiment. What if we, so Ezra is basically asking, we have now many samples on each side already, so why don't we just compute the basically the partition function of each side?
Yeah.
That's
Then compute so we have the absolute free energy, and then we compute the difference. And one way you could compute this partition function, right, is by taking a Gaussian as your base distribution, and then going from that Gaussian to your to the distribution of one side. So you have your Gaussian and your one distribution, and a Gaussian and your other distribution, and then you compute the free energy difference between the Gaussian and your one distribution, and then you have the absolute,
Yeah,
because
that
you know
would be
the partition
similar.
function. And
Or like,
you
I guess
require
the question is, yeah.
I mean, you require overlap from your Gaussian and your target. If you don't have overlap, you still need this approach to train, for example, diffusion from Gaussian to that thing, to the target. This doesn't like
regarding just take the samples to estimate, I would say I'm not sure about how rigorous it is, but it looks, if you just do Monte Carlo over a grade, then to estimate the free energy, right on A and B, and then calculate the difference. I feel like it's much harder. It requires more data, and I think we haven't. I think
you have limited or like it's not quite equilibrated or something like that.
Yeah, that's a good
Oh,
point
I
to
see.
test.
Okay, I misunderstood then. I thought you were saying that you just had like samples from the actual.
We do have close to it, but we only use like 5,000 samples. Oh, sorry, 50,000 or something, 20,000 or something like that. But I think it's a good point.
I mean, sorry, for the systems that you have here, it is possible to just compute the absolute free the absolute free energy and then take their difference. But if we have,
I think so. Yeah.
Respect to Gaussian.
No. If you just have your two alanine.
I think I think it's just like taking the grade over X and then have the free energy. Like.
Okay, I mean.
Yeah, we can give a reference to that, but yeah, I'm not sure how good it is, but I would say classically, when people don't use bar versus this, I would assume they save samples. So, but it's a good question. We can report something.
No, I mean, that's interesting to report in the paper. I'm just saying, because I mean, in practice, you couldn't do it. To answer Ezra's question, like for real systems, we couldn't. Or it would be much more expensive, basically, to go from the Gaussian to the distribution than to go from one distribution to the other distribution. So this kind of stuff also only makes sense if your two distributions are very similar, like this free energy difference computation. So if
yeah, I'm not sure exactly, but it just seems like if you do assume you have just samples from both sides equilibrated, then you could just compute the free energies exactly.
Yeah, if you have your small molecule inside the pocket, then you don't.
Okay. So I guess we're making the assumption that we do not have like totally equilibrated samples. So the drift that you learn is just like it's like a good guess that will steer your dynamics in the right direction.
And I think your one thing is also that you think your energy function is bad or biased, but now you have it is biased in a similar way, or the errors that you're making in one side of your simulation is the same or similar to the errors that you're making on the other side of the simulation. And then but I guess then it is fine. You also have the effect of these biases canceling out if you were to compute absolute free energy and then take the difference. Dokie. Any other points we should talk about?
I still want to ask, like, if you say that the system, for example, if you have a system like just say 100 dimensions, how possible is it to calculate the absolute free energy difference using, for example, grade or respect to Gaussian?
If you have a Leonard joint.
Let's forget about what specific system it is. For example, 100 dimension. How possible it is to use grade, because I think it's exponentially large, right? Even though you use 2, it's 2 to 100, which basically like it's crazy.
Oh, I see. I see.
The
claim is that it's easier to calculate the relative difference as opposed to computing two absolute quantities in high dimension. This is kind of the idea.
Yeah, I mean that's
okay. That makes sense. Yeah. Okay. All right. I think that answers my question.
Okay. Thank you.
But now the other thing is, right, my claim that we for alanine dipeptide, we can still do it. We can still compute the absolute free energy.
First I have to say alanine is not the hardest problem in our experiments actually. So we find actually even JMM 100 dimension and also LG is like harder things.
Okay.
But alanine takes more time to simulate. That's another. So it's like difficult from different perspective, I think.
Yeah.
But I still don't figure out how alanine. But perhaps you can project to a low dimensional space, like a series space, something like that, like 2-dimensional space, and you can do grid. Oh, I'm not sure. I'm just guessing how you can use this kind of thing. Because to me, even say 22 or 66 is already pretty large using like grid or Gaussian to have a good overlap.
Yup. Okie dokie. Then, should we conclude here? I think that's a yes. Okay.
Yeah. Thank you.
Then, thanks for the chat. I think this was super interesting.
Yeah.
And
Thank you guys.
thanks.
Thank you everyone for coming.
Thank you very much.
Bye.